It's time for Fun with Math, and we're back today with the lecture on derivatives and graphing part 2. And so remember, in part 1 we talked a little bit about how functions change, namely they increase or decrease. And remember that if the first derivative is positive, so first derivative is bigger than 0, we get the function increasing. When the first derivative is less than 0, the function is decreasing, which remember leads to these local minimums and maximums. And then when the second derivative is positive, we get the function being concave up, versus when the second derivative is negative, we get the function being concave down, which leads to this idea of inflection points when you have a change in concavity. And then we talked about how we use derivatives to determine these changes. We talked about critical points and the 4 steps. And in fact, we did the first 2 steps last time. So remember the first 2 steps. Step 1 was find the critical points of f. This is where f prime of x is equal to 0 or undefined. And then step 2 was a sign diagram for f prime. And if we did those 2 steps, then we could find where the function is increasing, decreasing, had local minimums or local maximums. Today, we're going to do step 3 and step 4. And so step 3 is just like step 1. It's find the critical points, but not of f, but of f prime. So that's when f double prime of x is equal to 0 or undefined. And then we'll do a sign diagram, but instead of doing it for f prime, we'll do it for f double prime. And we want to make a note here that all the inflection points occur at critical points of the derivative, just like all the local minimums and maximums occur at critical points of the original function f. So let's just do this. So last time, here's what we did. All right, we took this function and we did step 1 and step 2 to determine where it's increasing, decreasing, and any local extrema. And so that's in this blue box here. And so today, we want to determine where the function is concave up and concave down and find any inflection points. And we'll do this simply by doing step 3 and step 4. So let's see how this works. So let's write down step 3 so we can remember the process we're going to follow. So step 3, again, you're going to find the critical points. So find critical points. But instead of finding critical points of f, we'll find critical points of f prime. And so instead of f prime of x equal to 0, we have f double prime of x equal to 0 or undefined. And so we want to find f double prime of x. And remember, yesterday we found f prime of x. So here's f prime of x right here. Now I'm not going to take a derivative of this because you'd have to use the product rule. Instead, I'm going to use the derivative we found the first time, which is right here. So not the factored form, but just the polynomial form. So now I can take a derivative of this. So the 3 comes down, and I get 12x squared minus the 2 comes down, hits to 24, and gives me a 48x, plus the derivative of 36x is just 36. And I think I can factor out a 12 out of here, so I'll factor out a 12, and I have x squared minus a 4x plus 3. And I think I can even factor this thing, it looks like. So it's going to be 12, x plus or minus something, x plus or minus something, and I think it's going to be minus 3 and minus 1. And so there's my factorization. Now remember, it's defined everywhere. So this is defined everywhere. So you don't have to worry about it being undefined. And basically the derivative, the original function is smooth everywhere, so the derivative exists everywhere. And then it's equal to 0, so let's set this thing equal to 0. So 12 times x minus 3 times x minus 1 is equal to 0, where it's equal to 0 when x is equal to 3. So there's one critical point, and x equal to 1. So there's a second critical point. And so now that we found the critical points, what we can do is step 4, which is the sign diagram. And before we did a sign diagram for f prime, now we're going to do a sign diagram for f double prime. So right here, we'll write the sign diagram. We'll put our two critical points on here, 1 and 3. Critical points for f prime. And we're going to do a sign diagram for f double prime. And above it, we'll do sort of an analysis for f. And so what we'll do is we'll pick points in between and to the left, in between and to the right. So let's pick the point 0. That's a good point to the left of 1. Of course, the point 2 is the easiest point between 2 and 1, and the point 4. And what we'll do is we'll plug it into f double prime, and we'll use the factored form because it's easy to plug into. So we plug in 0, you get 12 times negative 3 times negative 1, which is positive. So we'll put a plus over here. And then if you plug in 2, we'll get 12 times, if you plug 2 in here, it's 2 minus 3, which is negative 1. And then times 1, which again, I don't care about the numerical value, I just care about whether it's positive or negative, and that's negative. And finally, I'll plug in 4 into that second derivative, because it'll tell me whether the second derivative is positive or negative. And so when you plug in 4, I get out 1 and 3, which of course is positive. Now this tells me certain information about the original function, because remember, when the second derivative is positive, the function has to be concave up. So I'm going to draw concave up here, and then when it's negative, it's concave down, and then when it's positive, it's concave up again. And then when you change concavity, remember you have an inflection point. So I'll write I and F here and put a circle around it. We change concavity here, so I and F here, and put a circle around it. And so now I can write down my sort of conclusion. So what's my conclusion? Concave up. So I'm concave up from negative infinity to 0. So I'm looking over here. Negative infinity, oh, not to 0, I'm sorry. Negative infinity to 1. So be careful there about those numbers on your number line. So negative infinity to this 1 right here. So negative infinity to 1, and then union 3 to infinity. And then I'm concave down in between, so from 1 to 3. And then I have inflection points. I have one at 1, comma, and then you have to plug this into the original, so 1 comma f of 1. And then 3 comma f of 3, whatever that is. So equal to. And to find those, you've got to come back up here and plug into the original function right here. So I don't really want to do that by hand, so I could plug in 1 and do that, and I could plug in 3 and do that. What I can do, though, is I can do this on my calculator. So take out your calculator, and we can graph this function, because we're going to need to draw the graph anyway. So y equals, I have x raised to the 4th, and then a minus 8x cubed, so 8x cubed. And then I have a plus 18x squared, so we're going to graph the original. And then I have a plus 7. And I need to make my window, so remember, the way you make your window is you look at all your critical points. So I had critical points for f at 0 and 3, and critical points for f prime at 3 and 1. So I'm going to go to the left of the smallest one. So the smallest one is 0. So when I make my window, I'll go -1. And then to the right, the biggest one was 3, so I'll go a little bit to the right, so that's 4. And then go to zoom, and then find zoom fit. We can just hit 0. And this will give me a nice looking graph. So I kind of know the shape of the graph before I even kind of start a little bit here. And so what I can do now is if I want to figure out what these points are, what's f of 1 and f of 3, I can just use my calculator, and I can make these computations pretty quickly. So if you plug in 1, you just hit trace and hit 1 and hit enter, it'll tell you the output is 18. So now I know I'm at 1 comma 18. So this is 1 comma 18. And this one's going to be 3 comma, and I just go down here to my calculator, hit 3 now, and enter, and I get out 34. So here I put 34. And so there is my information where I'm concave up, concave down, and where I have inflection points. So now what I want to do is I want to graph this information. So when you graph things, the easiest way to graph, remember, is simply to plot points and connect the dots. So you have a minimum f of 0 equal to 7. So when you plug in 0, you get out 7. And that's supposed to be a local minimum. So that's a min at 0, 7. And you can see that on the graph here, right here, that's probably the point 0, 7. So you can see that's a min. And I want to graph my other 2 points, which are inflection points, so 1, 18 and 3, 34. So I'm going to plot those on here too. So 1, 18, let's just put that right here. This is 1, 18. And that's an inflection point, so I'm going to write I and F underneath it. And then I have one more inflection point at 3, 34. So let's just put it right over here. We'll write 3, 34. Okay, and that's an inflection point, I and F. All right, so now what I need to do is I need to get this to be a min, and then I have to have this to be an inflection point, and this is an inflection point. So you can kind of see, like, for that to be a min, it's got to kind of go down and come up. So it's going to have to kind of come down, go through here, and come up. And then it's got to inflect, so it's got to change concavity. So then it's got to go concave down to here, and then it's got to go concave up again. It's got to change concavity. So then it goes concave up. I don't like that last one, so I'm going to redraw that last one. So then it changes concavity, it goes concave up. So it looks something like that. And you can check it on your graphing calculator to say, oh yeah, that's what it basically looks like. Now you're zoomed in a different way here, so it looks a little bit different, but that's the idea. It comes down, goes up, levels off, and goes up again. So it comes down, goes up, changes concavity here, then goes up again right there. Let's look at the next problem we did yesterday. So remember, we did step 1 here. So step 1, we found where it's increasing, decreasing, and it has a local min. Now we want to do step 2, or step 3. And so for step 3, let's write down step 3 again. So step 3, if we want to find the critical points, so find critical points of, now not of g, but of g prime. And so that's when g double prime of x is equal to 0 or undefined. And so we need to find g double prime of x. You'll notice last time we found g prime of x, so here's g prime of x. It's a quotient again, so we're going to have to do the low d high. So here's the low, 1 minus x squared, quantity squared, times d high, so times 2, minus the high, so that's 2x, times d low. So d low, it's going to be a chain rule, so that 2 is going to come down, times 1 minus x squared, and then it's the first power, and then times through the inside, which is a negative 2x. And that's all over your low squared. So 1 minus x squared quantity squared. So now we need to clean this up a bit. So let's clean it up. So this is going to equal, it's going to equal, let's write the numbers first. So 2 times 1 minus x squared quantity squared, and then minus, but it'll actually be a plus because there's a negative here, so negative a minus is a plus. And you have 2 times 2 times 2, which is 8. You have an x over here, and then times, oh, an x times an x, so you get x squared, and then times 1 minus x squared. And of course, that's all divided by 1 minus x squared. Oh, this needs to be squared again, right? So low squared. So remember, this is the low right here. Here's the low. It needs to be squared. So 1 minus x squared, and that's to the 4th, right? 2 times 2 here is to the 4th. And then we can factor out what they have in common. So let's factor out what they have in common. So on the top, let's see what you have in common here. So on top, we have a 2 and an 8. So it has a 2 in common. And then we have a 1 minus x squared squared, and a 1 minus x squared. So we'll factor out one of these 1 minus x squareds. And then we're left over on the inside with what? Well, this something times this is that, so we need one of these because we have a square here, so we'll need one extra 1 minus x squared. And then that's it. So this times this is that. Here you have an 8, we have a 2, so we're going to need a 4. And here you have an x squared, but you don't have any x squared, so you need a 4x squared. And anything else? No, I think that's it. So this times this should be that. That looks good. And of course you have the bottom is 1 minus x squared all to the 4th power. All right, so now what happens? Well, we can cancel off some of this. One of these will cancel with one of these, and so I'll leave us with 3 of those. And so we'll have 2 times, and then you have a minus x squared plus a 4x squared, so you get 1 plus 3x squared. And then I'll divide it by 1 minus x squared quantity cubed. So there's my second derivative. Now remember what we have to check out, what you have to watch out for. So you have to watch out for when it's undefined. And so when is this undefined? Well, that's when this denominator right here is equal to 0. So it's undefined. Undefined when? Undefined when 1 minus x squared quantity cubed is equal to 0. Take the cube root of both sides. And of course, 1 minus x squared is equal to 0 then. Cube root of 0 is 0. And so then this is, you can factor this, 1 minus x times 1 plus x is equal to 0. And so what do we get? We get 2 critical points for f prime, x equal 1 and x equal negative 1. And then the other possible critical points happen when the second derivative is equal to 0. So let's do that. Let's set this equal to 0. So 2 times 1 plus 3x squared, all divided by 1 minus x squared quantity cubed is equal to 0. And so to solve this is called a rational equation. And to solve it, we simply clear the denominators. And you'll notice the denominator just completely goes away on this one. So 1 minus x squared quantity cubed. We'll multiply this by that and this by that. So on the left-hand side, you just get the 2 times 1 plus 3x squared is equal to 0 on the right-hand side, because 0 times anything is 0. You divide out by the 2, and so we get 1 plus 3x squared is equal to 0, because when you divide 0 by 2, it's still 0. And so you may notice at this point that there's not going to be any real solution, because you have a positive thing here and a positive thing here because you're squaring it, and you can't add 2 positive things and possibly get 0 back. But you could solve it if you really wanted to. So we could continue here, and you could get 3x squared equal to negative 1 by subtracting 1 from both sides, x squared equal to negative 1/3, and so we wind up with x being equal to plus or minus the square root of negative 1/3, but that's an imaginary number, so here we have no real solution. What that means is that there just are no more critical points. There's only 2 critical points, 1 and negative 1. So now we're ready for step 4. So for step 4, we need to do a sign diagram. So a sign diagram for this case G double prime. And so we'll come down here, draw our number line. There's just 2 critical points for G prime, so negative 1 and 1. The sign diagrams for G double primes, we need to pick points to the left and in between and to the right. So maybe like negative 2 is good, 0 is good, and 2 is good. And so what we'll do is we'll do G double prime of negative 2, G double prime of 0, and G double prime of 2. And so we'll plug it back into that second derivative to see if it's positive or negative. So you plug in here. So on top, what you want to notice is that this thing will be positive always. So the top really doesn't matter. You can, because you're squaring it, it's always positive. So it's just the bottom that's going to determine the sign. So always have positive on top, always have positive on top. And that's because you're squaring this. So no matter what number you plug in, you square, it's positive, and these are all multiplied by positive, add a positive, multiply by positive. So it's the bottom that's to determine the sign. So if you plug negative 2 into the bottom, you get 1 minus 4, which is negative 3. And you're cubing negative 3, which is negative 27. So that's going to equal a negative number. If you plug in 0, you have 1 minus 0 squared, which is 1. And you cube it, you get 1. A positive divided by 1 is a positive number. If you plug in 2, you have 1 minus 2 squared, which again is 1 minus 4, which is negative 3, and you're cubing it, so you get negative 27, and so you get a negative number here. And then again, this is just me thinking, just kind of showing my work as I think this out. All right, so I guess I should put this all in quotes, because I'm kind of thinking it's not really mathematical, it's not like it's equal to this thing. And so what I have then is it goes negative, positive, negative. And remember, these are actually vertical asymptotes for the original function. So if you remember that, that's kind of nice. If you forget it, it's going to be okay in the end. You'll catch your mistake. But it's nice to remember those are vertical asymptotes, because what does this mean? So for g, we can write down what it means in terms of g. So when the second derivative is negative, it means it's concave down. So it looks like this. When the second derivative is positive, it means it's concave up. So it looks like that. And negative, it's concave down. So it looks like that. And when it changes concavity, remember you have inflection points, but you have to be careful. These aren't inflection points because they're vertical asymptotes. But again, you would catch it when you write up the analysis. So watch over here. If you try to write this analysis up, you'll say, okay, it's concave up between negative 1 and 1. So negative 1 and 1. It's concave down, or is it concave down? It's concave down between negative infinity and negative 1. So from all the way to the left to negative 1, and then from 1 to infinity. So union 1 to infinity. And then inflection points, if you thought there were inflection points at 1 or negative 1, what would happen is when you go back to try to plug these in to the original function, you'll see you can't plug in 1 or negative 1. It's undefined, and once again because you have vertical asymptotes. So for inflection points, you don't have to write anything down, or if you want, you can write down none. So there's my answer for its concave up, concave down, and inflection points. Now remember, what we want to do now is we want to graph this. And so to graph this, we need to plot the points that are given to us. So here we have a local minimum. When you plug in 0, you get out 1. So this is a local minimum. So there's a minimum at 0, 1. And let's write down min underneath it. And there are no other points. There's no inflection point, so you just have this minimum right here. But remember, you do have, this is important, you do have vertical asymptotes at negative 1 and positive 1. And so that's something you have to watch out for. And I know I have that. For one reason, I know I have that because over here at the original function, it's not defined at plus or minus 1, because if you try to plug that in, you're dividing by 0. So basically the function is going to blow up at 1 and negative 1. Now how it blows up, there's several ways to tell that. So the way that it blows up, what we can do, and we can just graph this on our graphing calculator. Right? So we have this y equals, we can clear out this one, and then we have 1 divided by, and then left parenthesis, 1 minus x squared. We can make our window, since we know all our critical points, negative 1, 0, and 1, we can do negative 1, or negative 2, sorry, just go a little bit left to the negative 1, up to 2. And then we can go to zoom, and we can try to zoom fit it. Sometimes it works with rational functions, but sometimes it's not a very good picture. This one's not too bad, though. So you can see what zoom fit looks like. So you see it goes down here, and then it comes down, and it goes back up. And it starts down and goes back up. So what we can do is we can kind of copy that picture, but realize it doesn't actually hit the origin. It comes down here, and that's actually the minimum value. So what we can do is we can just kind of copy that picture. Right? So it starts over here and turns around and comes down. So we'll do that right here. It starts over here, kind of like that, turns around, comes down, starts up here, comes down here, hits a minimum, turns around, comes back up. And then on the other side, you can see, starts down here, comes back up. So we'll start at the bottom, down here, comes up and starts to level off kind of right here, because remember there's also a horizontal asymptote. There's a horizontal asymptote right here at y equals 0. So you can draw that on there if you like, at y equals 0. And you can use your graphing calculator just to kind of check your work to make sure it's right. And you can tell from all this stuff, it's increasing from 0 to 1. Yeah, it's increasing. And 1 to infinity. Yeah, it's increasing. It's decreasing from negative infinity to negative 1. Yep. Negative infinity to negative 1. Yep. It's concave up from negative 1 to 1. Yep. So it checks all our criteria that we found. And so this is our graph for g of x. You'll notice in a lot of calculus books, they give several steps for graphing, but you really don't need all those steps. You just need these 4. And so hopefully it sort of makes some sense, sort of what we did here and sort of the purpose. So that, remember the idea is if I give you a function formula, how can we use the derivatives to figure out how to graph it? And then you can always use your graphing calculator to check to make sure that the graph is correct. But remember, you always need to know where to look, and that's what calculus helps us do. It helps us figure out where the critical points are. And so if the critical points are like 342, which isn't often the case because in the formulas it would look really nasty, but if it was in our formula, we would know where to look, and then we could easily graph it.